Hello. Welcome to day number 5. Day number 5. I trust that you guys had an amazing day. I had a holiday on my end, so I had a bit of time to rest and relax and to be able to pick up today's class, which I'm excited about. Before we start, just one announcement. On next week, our class is going to run on Monday instead of Tuesday. My son is going in for an operation on Tuesday, and I'm going to remain with the younger one at home. So not so sure if I can run a class without any interruptions. So just take note, the class next week is going to run on Monday, but next week, Thursday, we'll be back to the same usual time and date, and we can be able to pick it up from there. So I'll try and notify, I've got something scrolling up on the screen to be able to inform you to that effect. And later on in the class, I'll probably announce one more time for those that would have caught up with us a bit late. I am excited about today's class. As I mentioned on Tuesday, that the first few parts of Network Plus focus on the concepts. And sometimes concepts are not the most exciting of things to learn because you don't get to do, you just basically, let me just take away this. Just bear with me. I just need to just make some changes. All right, I need to take that, hide that, and then remove the banner from scrolling. All right. We should be good now. So I was saying earlier on that sometimes concepts, they are fantastic and amazing for us to know, but because you're not doing anything practical, it is not as exciting. But today I can finally say that we are getting to the part where we'll get to configure. So we're going to be covering quite a lot of practical demos in today's class. And I'm going to be using my normal tools, your Windows command line, but I'm also going to use Cisco Packet Tracer for some of the tasks that I'm going to be completing. You can download Cisco Packet Tracer. I actually encourage you to download it. It is a virtual lab environment that allows you to test multiple scenarios, and you can follow along as we go through. So what are we covering today? Today we're going to be looking at the network devices that we find on our networks and how those devices function. Things like hubs, switches, routers, proxy servers, firewalls. Why do we need them? What problem do these devices solve? And how do they do it? We are also going to be looking at our routing protocols. How do we route traffic on our network? Do we use static routes? Do we use dynamic routing protocols? And what are the different protocols that are available? So we're going to be looking at Ospf, Eigrp, BGP, RIP, static routes, default routes, all the exciting stuff. And then we're going to close off by looking at one of my favorite topics, which is quality of service. It was not covered in the past, but nowadays quality of service has become a key feature in any network. So it is important for you to know the technologies that are involved and how QoS basically works on a network. So without taking too much of your time, let us begin. Okay, so the first device that we're going to be looking at is a hub. If you've been in the industry for quite a long time, you've probably come across this device at some particular point in time. Nowadays, you rarely come across them, but from a physical perspective, a hub basically looks like a switch. So it is a device that has got network ports, and you plug your PC onto that. You can plug your printer, and it basically extends your network, and all these devices are able to communicate by connecting through a hub. You can also connect another hub to extend your network and extend the reach of your network. Now, the reason why hubs are no longer popular these days is because of the way that they function. A hub was basically known as a repeater in the fact that when packets got into the hub, it would broadcast to every port that is connected on that particular hub and propagate that information. And that in itself created a problem because the more devices you have on a network, the more broadcasts would be created. And that caused the network to be inefficient. So that was the first challenge that hubs had. The second one was that every device that was connected to a hub was in what was known as a collision domain. So there was, on a hub, there was only one collision domain. And in that collision domain, only one device could talk at any given time. Now, this was not a problem when you got 3-4 devices connected to a hub because you can wait for each other. The challenge then happened when you had a 48-port hub and you got 48 devices on the network and only one device can talk at any given time. Because if 2 devices try to talk at the same time, a collision would happen. And when a collision happened, all the devices had to then reset their timers and then try and communicate at a later point. So that created a network that was inefficient in the fact that the bigger the network became, the more inefficient hubs were then able to handle that particular aspect. So hubs have now transitioned into switches, and we're going to look at switches later on. The second device is something known as a bridge. Now, I have to be honest, in my entire network career, I've never come across a bridge as a singular physical device. And what I mean is that a bridge was used to connect. So back in the days, because of the hubs had an issue in the fact that anything connected to a hub was in one collision domain. And then also that one collision domain was also one broadcast domain, which meant that any broadcast that was sent to every PC or every device that was connected to the hub. So what the bridge basically came in to do was to separate and segment those two networks. So you could connect a hub on one end and another hub on this end, and then connect your PCs. And that bridge would then act as a boundary, making this one broadcast domain and this another broadcast domain. So if you had 48 ports here and 48 ports here, it basically meant that instead of having a 96 port collision domain, you now had a split network which had 48 and 48. That in a way lessened the impact of how hubs functioned. But because switches have come in to do this specific job, it has meant that bridges and hubs are no longer relevant into today's networks. As I said, in the last 20 years, personally, I haven't come across a bridge where I've seen it as just a singular device. So not only did the bridges segment network, they were also intelligent enough to filter frames as they traversed through the bridge, and they also acted as a repeater. And the repeater concept comes from the fact that UTP cable has a limitation of 100 meters. So by putting a bridge in between, you could run 100 meters on this end and run another 100 meters on this end. And your networks could then connect on an end-to-end of 200 meters because the bridge acts as a repeater, meaning it takes the signal and it boosts it and increases the strength of the signal, making it capable of running another 100 meters. So in situations where you might have had two buildings that needed connectivity, but the distance between them was 150 meters, you could find a location where you would plug in a bridge, and then you'd connect a switch, and the switch and then you could then be able to bridge that distance and take care of the 150 limitation of UTP cable. So that was the function of the bridge. But like I said, I've never encountered it. What I have encountered with switches, and we're going to be spending a bit of time explaining how switches function and the different concepts that are involved when you're dealing with switches. Let me just get this right. Okay, cool. Okay, so switches are layer 2 devices. They operate on the data link layer. Remember when we spoke about our OSI? Let me just get my pen right. Okay. When we spoke about our OSI, at the bottom we had the physical layer, and then after that we had the data link layer, and then we had the network layer. Switches are layer 2 devices, and they forward frames, and they deal with MAC addresses. And we say that the MAC address is an identifier for network devices, and there's no two devices that have the same MAC address. So switches learn about those MAC addresses, and they make decisions to forward frames based on those MAC addresses. Now, the behavior of a switch, I'll just draw this, and I'll probably just put 1, 2, 3, 4 ports. So when devices connect to a switch, this PC1 sends a packet trying to talk to PC2. When that frame gets to the switch must know the MAC address of PC2 in order for it to know how to forward that particular frame. In the event that the switch does not know the MAC address of PC2, a switch then floods that request to every port on the switch except the one that it received the request from. And this is the process of how switches learn about their MAC addresses. And we're going to go step by step in the next slide, covering that whole process. We're also going to look at it practically in Packet Tracer and see that whole process in action so that we've got a full understanding. Remember, the core focus is for us to get the practical skills rather than just knowing the theoretical concept and knowledge. So I'm just going to take us to the next slide, and then I'm going to explain the process, and then we're going to look at it practically. So in our case, we've got PC1 sitting here, and we've got, this is our server, right? So we've got our server that is sitting on this end. This is switch number 1, and this is switch number 2. And we are starting with the MAC address table being clean. The switch does not know anything about any devices that are connected to it. So if PC1 wants to talk to the server that is sitting here, maybe it wants to do a remote desktop session, before it can talk to that particular server, it's going to need two things. It's going to need the IP address of the server, and it's going to need the MAC address. And why does it need the MAC address? Remember, the IP address is level 3, MAC address is level 2, and then you've got the physical layer where it's got the bits that then get sent over the wire to get to the destination. So in our case, let's say the server IP address is 10.0.0.10, right? So we've got the IP address, but we don't have the MAC address. So the switch, the PC then makes what is known as an ARP request, which is an address resolution protocol. So it makes a request asking the switch for the MAC address of the server. So it is going to send a frame going towards the switch. The switch is going to receive the frame, let's say on gig 0/0. It is going to receive the frame on gig 0/0. Now the behavior of a switch when it receives a frame is that if it doesn't have, so let's put here gig 0/0, this is going to be gig 0/1. If the switch does not have the MAC address of the device, it then registers the MAC address as the device enters gig 00 or enters an interface on the switch. Why? Because this frame is going to contain a source MAC address of PC1, and it's going to have a destination broadcast of FFFFF, which says send to everyone and tell me who has the MAC address matching that particular IP address. So the switch will then look at its MAC address table, and if it doesn't find the MAC address of the server, by behavior, it is going to send a frame on all ports that on that switch, except the one that it received the request from. So it won't send in this direction. So it's going to send up, down, and it's also going to send to switch number 2. Switch number 2 is going to receive a broadcast request with a value of FFF, and it will do the same thing. It will forward on every port that's connected to that particular switch. And then when the server then receives that request, the server is going to say, oh, by the way, I'm the one who has that IP address, and my MAC address is going to be 2222222. So it will then respond back with a frame, and in that frame, it is going to put its source MAC address of 2222. When it hits switch number 2, switch number 2 is going to record that gig 0/2, which connects to the server, has a MAC address of 2222222. And remember, when the packet got into switch number 1, it registered that the MAC address of 11111 is reachable on gig 000. Switch number 2 is going to then send the response back to switch number 1. And then when switch number 1 receives that, it then realizes, oh, by the way, the MAC address of 222 is known via gig 01. So it's going to register 222 in its MAC address table, and then it will then reply to PC1 and notify PC1 that the MAC address of 10.0.0.10 is 22222. And then when PC1 then sends a message, it will then send it with now the correct source and destination MAC address. And that is how switches learn about MAC addresses. It's a multi-step process and might not seem very clear, but this is what basically happens. So later on, and I just need to put gig 0/2, and then it will learn about gig 0/1. That's when it will learn about the 111.111 MAC address. So whenever the switch has got the MAC address in the MAC address table, any future requests, it will just look at its MAC address table, and if it has the MAC address of the device in question, it will forward the frame out the interface where the MAC address is known. Now the MAC address has a timeout period, right? It's not going to be stored forever. The reason being that if it was stored and was not deleted, it means every device that the switch ever connected to, it's going to retain the MAC address, and that will consume memory on the switch. So most switches, if not all, have a timeout period where after about 600 seconds, which is usually 5 minutes, I think that's the default on Cisco devices, it flushes out its MAC address table, and that then allows it to learn more MAC addresses. And the PC basically does the same thing. So I'm just going to check if there are any questions before we then go into our lab to be able to then demonstrate this particular process happening in action. Okay. All right. There are no questions, so that's good. So what I'm going to do is I'm going to pull out my GNS3, sorry, packet tracer. I'm going to pull out packet tracer and just ignore this lab. We're going to look at this lab at a later point. So I'm just going to delete, and I'm going to reconstruct this lab from scratch, and we're going to go through it together so that we can be able to see this whole process in action, and it will be easier for us to learn. So with Packet Tracer, it's a Cisco tool, fantastic and amazing tool. I would actually encourage you to download it. And at the bottom of Packet Tracer, you've got the option to pick the devices that you want. And in our lab, we're going to simplify things. We have PC, and then we're going to have a switch. So I'm looking for network devices. So I'm going to have a switch. So my PC is going to be here, switch. I'm going to need another switch. And then let me see, another switch, that's correct. What else do I need? I'm going to need a server. So we're going to put our server here. Let me just take the server. Okay, so we've got all the devices. Maybe I'm going to put another PC just so that we can be able to see the action of everything else that's taking place. All right, so we've got that. And then I need to then connect my devices. There's this icon in Packet Tracer that looks like a lightning bolt. It just allows you to then make connections automatically. So you come and click on a device. Yeah, there we go. So that will make my connection from here. I'll click on that to connect PC4. And then I'm just gonna just try not to zoom too much. And then I'm gonna connect switch number 2. And then we're going to connect our server. All right, so that's just about it. We're going to configure IP addresses. And in our case, we are going to use 192.168.0/24 as our IP address. So to configure, you can come to desktop, go to IP config, put a static IP address of 192.168.0. We're going to call this 1. It's going to have a subnet mask of 255. That should be good enough. I'm going to close that. I'm going to do the same thing on PC number 2. We're going to give it an IP address, and it's going to have an IP address of 192.168.0.2. Same mask, so these devices belong to the same network. And then what do I need? I'm just going to do this in real time. And then the last one, this is the server. The server is going to have an IP address of 192.168.0.10, and that will be on a mask of 255.255.255.0. Okay, so our lab is almost good to go. This just broke a little bit. Okay, cool. Our lab is almost good to go. So we're going to start with PC1. Right, we go into the command prompt of PC1. We just want to make sure that we know the MAC address of PC1. And the command to do that, this is similar to what you do on a Windows machine. So the command to do that is ipconfig PC4/ALL, and scroll down, you should see the physical address. So PC3, the MAC address ends with C174. So we just want to note that. Let me see if I can take a pen and say C174. That's going to be PC3. And then let's look at the the MAC address for PC4. Again, ipconfig/o. And then let's need to expand this. And this one is C1C08. So PC4 is 1C08. We're just making sure that when we see these MAC addresses, we will know where they're coming from. That's the only purpose that I'm writing that down. Okay, so let us now go to our switch. Let's see what the switch knows in as much as the MAC address is concerned. So we're going to go into the command line interface of that particular switch. And this is what the switch can see. So press enter, enable, and the command we're going to type is show MAC address. So the switch has come back to us, and it's saying it only knows about one MAC address, which is E701. Now that is not PC3's MAC address. It's not PC4's MAC address. So let us go and check the server to try and see what the MAC address of the server is, so that we can be able to then, understand and be sure that the MAC address that we're seeing is not of the switch on the other side, but it is of the server. So we're going to go to the server, the services here. Can I see the command line? Okay, there we go. ipconfig/ALL, and that is, so the physical address of the server is E2, E6. So the MAC address that we're seeing so far is the MAC address of the other switch. So this switch does not know the MAC address of any of the devices, because when you look at the MAC address table, just going to go up one, there is nothing in the MAC address table. There's only one MAC address, which is the MAC address of the switch on the other end. So we are going to then initiate a packet request from PC3 trying to get to our main server. And in the process, PC3 is going to make an app request. And in the app request, it's going to learn the MAC address. So one more step before we start. If you go to PC3 to check the app table of PC3, the command is app -a. So we press enter, and we can see that there are no entries in that PC's app table. So we are going to make a request. And the beauty about Packet Tracer is that there's something known as a simulation, which then allows you to see what is happening on the wire. Sorry, I might have just lost. We bring my Packet Tracer one more time. Okay. So we can run this in a simulation mode, and simulation mode allows us to see the packets that are being sent and what is being sent. So I'm going to enable simulation mode. If you see on this bottom right-hand corner, you're going to start seeing packets basically flowing through as I make the request. So I'm going to go to PC3, and I'm going to ping the IP address of the server, which is 192.168.0.10. And I'm going to press enter. So now you are seeing a packet that is leaving PC3, and that makes it to the switch. And it is going to make a request for the MAC address. And because the MAC address is not known, it sent a packet on FA02 and FA03. And when you go to switch number 2 did not know the MAC address, so it also forwarded to the server. The server then responded back, and now we see the packet coming back to switch number 2, and then switch number 2, and that's an app request. Switch number 2 then forwards back to PC1 to notify him of the new MAC address. Now I'm going to pause this, and I'm probably going to take off the simulation mode, and I'm going to go to real time. If you want, you can actually go on the right-hand side you've got the ability of being able to see what was happening at each and every stage. So the first packet that came through was a layer 2 frame that had a source IP address of C174, which is the IP address of PC1 in our lab. And it had a destination of FFF, which means it was a broadcast frame looking for the MAC address of this IP address 192.168.0.10. So it's simply saying, who is 192.168.0.10? And it broadcasts. So that frame gets forwarded. And then when that frame hit the switch, which then happens here, we are told that the switch received the frame. But because the switch did not know the MAC address of the server, it then forwarded to everyone else as the normal behavior. Now, earlier on, when we looked at the app cache of this particular PC, there was no entry, as you can see here. But this time around, when we do app-a, you're going to find that now we have an app entry of the 192.168.0.10 IP address, and that has a MAC address of E2, E6. So now PC1 now knows the MAC address of the server. So any subsequent packet that it wants to send, it will then forward that information to this physical address of the server. And then when that frame gets to the switch, what is the switch going to do with it? Let's look at the MAC address of the switch. Earlier on, our switch had only one entry in its MAC address table. This time around, when we press that, we now know that the switch has 3 entries. What are the 2 new entries that the switch received? The first one was the physical address of PC1, which is connected on port F01, which is this port. And then the second one was the MAC address of the server, which it learned from port F03, which basically connects to this particular switch. And then if we go to this switch and look at its MAC address table, show MAC address table, you'll notice that the switch has an entry for our PC, but it is known on port F01, which is the port that it connects to this switch, and the server's MAC address of E2, E6 is known on F02, which is the port that the server is connected to. So this is how switches learn about frames. And it is for this reason that switches are more intelligent than hubs. That's the first thing. The second thing is switches are, each port on a switch is its own collision domain. Remember, on a hub, every port on a hub, if it was a 48-port hub, that whole hub would be one collision domain, and only one device could talk at a time. But switches, if it's a 48-port switch, it will have 48 collision domains, because each port on that switch is its own collision domain. So all devices can talk at the same time without any interference, because they don't belong to the same collision domain. So that's how switches are basically more intelligent than hubs. And this is how switches learn about MAC addresses. And that is the MAC address table. And we can query it on Cisco devices, type in the command show MAC address, and we're able to then see whatever is taking place. So try and lab this in your own spare time. Try and have a look and see how switches work, and practice. The only way you can learn is through practicing. So you can clear this MAC address table, and you can force the switch to learn this MAC address table one more time. And the command for clearing the MAC address of a switch is clear MAC address, and that's it. And when you go up and show the MAC address table, once again, the MAC address table is empty. I wouldn't encourage you to type this command in a production environment because you create an outage, because all the devices then have to go again through the process of trying to learn the MAC address and all packets being forwarded across. And in a network with multiple devices, that will probably cause an outage, and it will still come back. It might take a few minutes to come back, but yes, it's a very bad command to type in production, especially if you type it on the core switch and then you wipe out everything that the core switch knows, and it has to learn again. So let me just minimize this, and let's go back to our slide. Okay, so let's go back. Okay, so basically the process that we explained earlier on, that's what we saw happening in a live environment. Let's get that. So we have looked at hubs, we have looked at bridges, we looked at switches. The next type of device that we're going to look at is a layer 3 switch. We said normal switches operate on layer 2 and they deal with frames. But layer 3 switches have the capability of operating at the network layer, which is known as the layer 3. And this is where you deal with IP addresses. So with the layer 3 switch, you've got the ability of being able to configure an IP address. And that IP address then allows you to then segment your switch into multiple broadcast domains. Because by nature, a layer 2 switch, even though it has multiple collision domains, it is still one broadcast domain. So any request made to a broadcast address is forwarded to every port on that particular switch. But with the layer 3 switch, you can create a broadcast boundary by implementing a layer 3 interface, which basically stops broadcasts, because by very nature, broadcasts are not propagated on layer 3 devices. So layer 3 devices break broadcasts. So layer 3 switches, you'll find them in organizations. Sometimes they are placed in the distribution layer of the network architecture. Remember last week or last lesson, we looked at the 3-tier system. We said we've got the core switch, we've got the distribution, and then we've got the access switches that then hang off on the bottom. Most of the times, your distribution switches are capable of layer 2 and also layer 3. Layer 2 in the fact that you need the ports that the access switches connect to, and then layer 3 in the fact that you can be able to then create point-to-point IP links between your core switch and your distribution switch and implement routing protocols on that particular part of the network. So you will encounter them, but usually you'll find them in the distribution tier of your network. So we've covered that. The next is an access point. Access point, because most of us deal with wireless devices nowadays, access points are basically simple to explain. An access point is basically a device that provides wireless connectivity to endpoints on a network. And then at the back end of the access point, it then connects to the network via a cabled backbone. And wherever you're connecting to a network, either your home network or in the office, using a mobile device where you don't have any cable connected to it, you are connecting via an access point. The access point will then take those radio signals and then converts them into the back end bits, which are then sent to the switch. And there are two types of access points that you find on the network. The first one is known as an autonomous access point. These access points are also known as standalone. They do not need a wireless LAN controller to manage them. They have the capability of managing themselves. Typical situations are your home router that you got from your internet service provider. It will come with 4 ports plus or minus to connect your network. It will also then connect to an NTU or modem that comes from your provider. And then it also has 2 antennas for your wireless access. That is an access point that is acting as a standalone. It does not need any other device in order for it to function. The second category of access points are known as lightweight. And these lightweight access points cannot operate independently. They need a device known as a controller to manage them, right? So it's like a server in the back end. So everything that they need to do, they talk to the controller and the controller pushes the instruction. Instructions tells the device what SSID to broadcast, tells the device what strength to use. Everything that it needs, it goes to the controller because the controller manages everything. And not only does it manage, it also monitors the performance of those access points. And in a corporate environment, this is the more preferred topology or technology for wireless because it allows for centralized management. This one controller can actually manage plus or minus 5,000 access points, and you can manage them from one central location as compared to trying to manage 5,000 single individual devices that when you make configurations, you have to go to each and every 5,000 devices and make changes. If you want to change a pre-shared key, you have to go to 5,000 devices, which is not practical in a corporate environment. So we use lightweight access points, and you only need to change the pre-shared key on the controller, and then the controller pushes it to all the other devices in the network, and then they get updated in that context. So when you get into a work environment, look in the ceiling, you're probably going to see one of these white devices, either Cisco or Ubiquiti or Unify. 90% of the times, they're going to be using a controller compared to them being an autonomous access point. So those are the 2 access points, and that's what you're basically going to encounter when you're dealing with autonomous access or lightweight access points. The next device is a wireless LAN controller, which I've basically explained. It is basically a server that sits in the back end that then controls access points that are connected on the network. What that does is not only does it push config, but it also monitors. And how does it monitor? When you're dealing with Cisco access point, there's something known as zero-touch configuration, and there's something known as black self-healing access points. Yes, this is the word I was trying to look for, self-healing. And what self-healing technology basically does is that you got an access point here, you got an access point here, you got an access point here, and then this is the area that they cover of the network. And if any of them was to go down, this then becomes a black hole. So with Cisco self-healing, it tells this access point to increase its strength so that its circle becomes a bit bigger, and it tells the same for this, and it will then fill up all these areas that were left blank by the other access point. And the only way it can achieve that is because the same controller is one that's managing the access points, and it detects that something has gone wrong. So there is huge benefit in having a wireless LAN controller in your network, managing your devices, and being able to push config from one location instead of going to configure multiple devices just to achieve some change in the network. So that is our wireless LAN controller. The next one is a load balancer. And from the very word load balancer, it is a device that balances the load on your network. Now you're wondering, well, that doesn't make much sense. Okay, let's look at an example. So let's take Facebook as our example. Let's say Facebook has got 5 servers that serve content, and this is our load balancer. So the Facebook website will be resolved by the load balancer. So when you are coming in from different directions, you are not hitting the actual servers. The servers are sitting behind the load balancer. The load balancer is acting as your front point. What the load balancer then does is whenever requests come, it will then forward the requests to the different servers based on usage or based on which server is not doing much at that particular point. So if this server is probably sitting at 90%, instead of forwarding more requests, it will find another server that's probably sitting at about 30%, and then it load balances that particular load across the different servers. So load balances are there for performance. They're also there for high availability, because if one server was to go down and go into maintenance, the load balancer just stops forwarding messages to that particular server, but still load balances across other servers that are still functional. So if you were hitting the servers direct, then you'll have a problem, because then you can't take the server out of production because people are connecting to it directly. So they serve that particular purpose, and they're very good for web applications and web servers. This whole concept of load balancing. The next is proxy server. Now, a proxy server, for those that are aware, a proxy server basically takes requests. So this would be our proxy. And we've got a PC sitting here, which is PCA, trying to go to the website that is sitting on 8.8.8.8. So PCA, instead of going direct, he goes to the proxy. The proxy notes down that request, and then the proxy then establishes a session with the server on behalf of PCA. And then whenever it gets any responses, it then sends back to PCA. And the reason why proxies do that is, the first one is security. You can protect your internal network because what is known to the public is going to be the IP address of the proxy, and the numerous PCs that are making requests to that proxy are going to be protected, because then they are not exposed. If someone was to attack your network, they'll only hit the proxy server, but they can't get to you because you're sitting behind the proxy. So proxies are usually good for security. The other reason why proxies are used is for content caching. And how does that happen? I'm going to take a deep breath, and I'm probably going to try and explain this in this example. So let's say Australia as a country connects to Netflix servers, right? So they're trying to get to Netflix servers, and let's say we have a big proxy in the country. So we send all our requests to this proxy server, and this proxy server then talks to the Netflix servers on our behalf. And I don't watch Game of Thrones, but let's say Game of Thrones has come out. So everyone else in the country wants to watch Game of Thrones. So the proxy server only needs to get one copy of Game of Thrones. It sits on the proxy as cached content. And anyone who then connects to that proxy, instead of them going to Netflix to try and get that content, because it had already been cached by the proxy server, they then get a faster response because the proxy has already cached that information. So in a business environment, in a corporate environment, how this scenario would basically play out is you got a branch office and then you got head office, and there are file servers that are sitting in the head office that users from the branch access. So when people open specific documents, and if we are using a proxy on this location, those documents get cached on the proxy sitting at the branch server. So when someone tries to open the same document, instead of them going over the WAN to get to the HQ office and pull out that whole entire document, they can then get content from the cached document that is on their proxy server, which then speeds up the process. So in a way, proxies then become performance enhancing devices, in that particular context. I've seen this working mainly at universities. I once managed a network for a university that was in Papua New Guinea, and the internet in that location wasn't very good. And when you got multiple students trying to access the same YouTube videos for related content, the proxy server comes in very handy, because then it caches that information, and then the 10 other students that go after the first one don't have to then pull that information straight from the server. They can access it locally. And the third use of a proxy is content filtering. So you can configure your proxy to filter certain websites that you don't want people to go to. And when someone makes any requests to those respective websites, it will then deny that particular request. And that was also a very good tool for university, because then you would filter certain websites that are not productive websites that people should not be going to. You know the ones that I'm talking about. I'm not going to say them here. Anyway, so let us see how this proxy works in action. I'm just going to erase that. Return. I'm going to pull my web browser. And today I'm happy. I want us to do things practically. I don't want us to do things theoretically. So I'm just going to check to make sure that you can see my screen. I don't need this guy out. All right, where is that? Where is that web page? Okay. All right. So there are these web proxies that you find on the internet, right? So if you wanted to go online, but you don't want people to know who you are, where you're coming from, and you want to hide your identity, you can use a web proxy. So if you want to pirate content, download videos, and hide your identity, you can go to some of these web proxies. They're very simple to find. So I just went on YouTube and I just typed web proxy, and I clicked the first one that came up. And this one comes up, and then it will ask you to type your URL of where you want to go to. Now, before I do that, I want to show you something. So this is my normal web page, web browser. It's not proxied. When I type what is my IP address, I said this before, that when you type this command, it will give you your public IP address. And in my case, my public IP address is 49.192.53.254. I want you to note down that IP address, because when we run the same command with the proxy, you notice that that IP address is going to change, and it's going to be something else depending on where the proxy takes me. So I'm just going to go and pick a server that is sitting in the US. Right, so just pick that random server, and then let's go to google.com. So when I press enter, this page is now running behind the proxy. So whatever I do, the endpoints are not seeing my actual IP address. They're seeing the proxy's IP address. So let us type that command again. What is my IP, and press enter. And you will notice that the IP address that came out this time around is totally different to the one that we looked at earlier on, right? My original IP address is 49.192.253.254, and the proxy IP address is 68.235.61.121. So the proxy is, so let me draw what has basically transpired. So this is my, there we go. This is my PC, and I'm going through a proxy server, and that proxy server is then taking me to the internet, taking me to the Google webpage. So the proxy is now hiding my identity, and it is providing its identity to the outside world of this IP address, and my IP address has basically been hidden. And I'm probably just going to close that off by then asking what is the time. Let's see, what is the time? Why can I not? Okay, there we go. What is the time? I want to find out what the time in that location is. On my end, my time is 9:54 p.m. and the location that it took me to is in the southern part of the United States, and the time is 9:54 a.m. So 2 different time zones. So I'm proxied and I'm showing up to the world as if I'm coming from the US, but I'm sitting here in Australia. So if you want, you can use web proxies to be able to safeguard your identity when you are communicating on the internet. And we're going to close off this section by looking at the 2 devices, which is, put my keyboard here, the firewall. All right, so firewall. So we looked at proxy, firewall. Just trying to draw a firewall here. All right, to look something like this. So your devices on the network connect to the firewall. The firewall then takes you to either your router and takes you to any parts of the network. And what a firewall basically does is protect your network. I'm going to come to your question, Ceci, in a minute. So your firewall protects your network, and how it protects your network is that as traffic passes through the firewall is going to filter and permit traffic based on the rules that you basically apply. There are 2 types of firewalls that you're going to find. The first one is a stateful firewall. And how a stateful firewall operates is that when PC1 makes a request to an FTP server sitting here, the firewall only needs 1 rule, which is permitting of the traffic coming from the inside of the network. So this part is the inside, and this part is the outside. So as long as the session has been initiated from the inside, going to the outside, the return traffic is going to be permitted. Why? Because the firewall is tracking statefully the sessions that are taking place. So it's simply saying, I allowed you to go out. The reply of that traffic, I'm going to allow it to come in without filtering it or stopping it. Firewalls then also deny by default any traffic that's coming from the outside of the network. So anything coming from outside, it's denied, unless if there's a rule that specifically allows the traffic to go through. But traffic coming from the inside, it's permitted, and then the return traffic is usually permitted on the basis that it was seen going out. The second one is stateless, and a stateless firewall means it doesn't keep the stateful information. So you need to permit traffic going out, and you need to permit traffic coming in. Otherwise, they will not basically flow as they go through. All right, so let's go back to the question. What is the name of the application you used for the simulation and illustration of MAC addressing? It is called Cisco Packet Tracer. Actually, let me do this. Let me erase that. Let's pull out web page and let's go to the Cisco website. I'll just get my keyboard. So if you go Cisco Packet Tracer, I don't like the process that it takes for you to, if you go to the netcad.com academy, you will be able to find out about Packet Tracer. And then Cisco requires you to create a login in order for you to download it. So you need to just create a login to any of these courses that they provide. And then after that, you can then be able to download it, and then you can install it. Brilliant tool. Encourage anyone to install this, and any subsequent videos when I'm doing practice labs on networking concepts, we're going to use it in routing. I'm going to use Packet Tracer because it is readily available. It has got all the tools that can enable you to be able to practice and be able to learn. Okay, so back to, all right, one step backwards. So we've looked at firewalls, and the last one is IPS and IDS. And IPS is intrusion prevention, and then there is intrusion detection. And what these devices basically do is they detect malicious attacks or malicious traffic that is flowing through your network. And depending on which device you've used, IPS or IDS, they're going to then behave differently. So what does IPS do? So let's take your PC is sitting here. You've got your switch, and then you've got your router, and then you've got the internet, right? So anything that's coming through is coming from the internet. The IPS devices are usually not placed in line of your traffic. And what do I mean by placing a device in line? If you look at my switch is in line, meaning anything that's coming from my PC going to the router has to pass through the switch. And then the switch is going to forward that traffic onto the router. And there's no way I can go and bypass the switch because the switch is in line. An IPS device is usually not placed in line. It is placed on the switch, and then it analyzes traffic as it traverses your network. And then it produces reports of what is happening with that particular traffic. If there's any anomalies that are taking place. So because it's not in line, it can't take any action. So usually what they usually do with IPS is that it mirrors this particular port. So everything that's coming out here is also sent to this IPS device. It analyzes, it produces graphs, saying to you at this time of the day, the packets went 1, 2, 3, 4. So an IPS device identifies but does not. So IDS is the one that identifies but does not act. An IPS device is placed in line. So then it is able to then take action based on whatever it finds traversing through that particular network. So I just need to get the right definition, and I'm just gonna move my mouse. Okay, yes, I wanted to get to that point. So there are 3 ways in which IPS and IDS devices learn about abnormalities on your network. The first one is through signatures. The second one is through policy. And the third is through anomalies. And I'm going to explain the signature part. So the signature part is that when malware or malicious traffic is generated by the hackers who are trying to compromise your network, in that traffic, they try and find patterns, right? So that's where the signature comes through. They try and find patterns. And the best that I can basically be able to describe as patterns is safety at night, right? So safety at night, one of the common tricks that most of these car hijackers usually do is you're driving, they stand on a bridge, they throw an egg on your windscreen. So when they throw an egg on the windscreen, what's your initial reaction? It's to turn on the wipers. And then by turning on the wipers, you then spread that cracked egg on your windscreen, causing you not to see the road. And then you're forced to stop. And in the process of you stopping to try and fix it, that's when they will come and then hijack your car. So on news or on Facebook groups, whatever information outlet you subscribe to, they usually then say, oh, there's this form of hijacking that is taking place. So next time when someone throws an egg on your windscreen, don't turn on your wipers. Just continue driving until you're in a safe location for you to then, take that egg out. So what you're basically doing is you're establishing a pattern on how these thieves or hijackers are behaving, and you are passing that information so that people don't fall in the same trap. That is the same thing with signatures. So what signatures basically do is, in the packet that these malicious content is being sent, there's a pattern that is there. So they'll create a signature of that pattern, and then that signature is then forwarded to firewalls and intrusion prevention and detection devices, so that the next time they see a signature that matches the signature that they have, they can then deny that traffic based on that particular signature, because it will then be considered as malicious traffic. The second way is policy. Policy is where you decide, I want you to permit A and deny B. So when the device sees anything that matches A, it's going to deny it based on the policy of the device. And the last one is anomalies. And anomalies, I would like to put it across as a baseline. So your network is going to take a baseline of your network performance over a period of time. So 7 days a week. It says, okay, fine, Monday to Tuesday, Wednesday, Thursday, Friday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. This is the behavior of the network, right? And this is my speed. Maybe my network average is 10 Mbps per hour over that period of time. And then all of a sudden, when I have malware that's running, maybe something like this happens. And all of a sudden, I'm hitting 100% network usage. And that is then considered as an anomaly. And depending on what you have configured as your reaction, it can either shut down, stop traffic, and react because something has happened that is basically different. So those are the three ways that our security devices, sorry, they're not the only three ways, but those are the three most common ways in which how our security devices then protect our devices on the network. The only challenge with signatures is that they have to be downloaded, and you have to constantly have the most recent signature, because if some malware has come out or some threat has come out and you don't have the latest signature, it means that your network is going to allow that traffic to flow through because you don't have a signature that then tells you to do otherwise. So it is important for you to then understand. So these are the most common devices that you'll find on your network. And we're just going through how those devices work so that when you encounter them, you don't have to get stuck in not understanding on how they basically function. Okay, so now we're looking at the we're looking at the network devices. Now we're looking at the networked devices. So these are the devices that connect to our network. Let me just go. Okay. So the devices that connect to our network, we have IP phones, and IP phones basically convert packets they convert voice traffic into packets that can be transmitted over our data network, and that basically flows through. But there are a few terms that you need to know when you're dealing with VoIP, which is basically voice over IP. We've got the IP phone, which is the one that then handles the receiver handset talking to the user. We have the call manager, because most VoIP devices need the call manager to be able to manage, just like we do with access points. And when we are talking between the call manager and the IP phone, we use a protocol such as SIP, which is a session initiation protocol or initiating protocol. So what SIP basically does is that when you press a digit here, the phone talks to the call manager via SIP and says, someone pressed 1, what do I do? The phone says, okay, wait a few minutes, few seconds, and let's see if they're going to press another number. So they're going to dial 999. And then from there, the call manager decides whether this 999 extension is connected to another phone that is local to your office. If it's connected to a phone that's local to your office, it sends a message telling this phone to ring, and this phone rings, and then the call is then established. When the call is established, then SIP comes out of the picture, and then RTP comes into the picture, which then basically handles the real-time packets as they're traversing through your particular network. The second device is a voice gateway. Now, the old PSTN system, where you had the analog phones, operated differently, and now we've got the voice over IP, which is operating on the data network. You need a device that translates between the two technologies, and a voice gateway is that device. So what a voice gateway does is that it has one leg on the data VoIP side and another leg on the PSTN. And when it receives requests, depending on the number that you're dialing, it either sends you to the respective network that is then able to allow you to then be able to communicate. So voice gateways, IP phones are devices that we find on our networks. We also find printers. I don't have to explain printers. They're pretty simple. We connect to printers so that we can print. We've got network printers that are on our network. Some of the uncommon devices that you probably find, which are becoming more prevalent on the network nowadays, is devices known as HVAC. And these are your devices that manage your cooling or your heating. And they've got sensors. And depending on how the temperature is either going up and down, they can either take action to kickstart the what do you call these? The cooling devices to either kick in, or if it's getting too hot, it takes that particular action. And this one has now been prevalent in networks recently, which is IoT devices, which is the Internet of Things. You've heard about IoT devices, and you've got things like your smart speakers, things like Alexa. Alexa is an IoT device. Yes, Alexa. I don't think I know any other. I think Google has got its own version of that. You've got your smart doorbells that have a camera, and when someone rings the doorbell, you can answer the doorbell from your office and give them instructions of where to leave whatever package or whatever they're looking for. You can be able to help them. You got smart fridges that have the ability of being able to connect to the supermarket and then order groceries when certain quantities start depleting in your fridge. All these devices need to connect to our networks, and our networks must be capable enough to be able to handle this increase and demand, which is why I said in the last lesson, we were running short of IP addresses because all the devices need IP addresses in order for them to communicate, and IPv4 had no capability to support multiple devices. Other smart devices that are coming in are EV, electrical vehicles, that download software onto the car and they get uploaded just like you update your PC. And all these devices need to connect to our network in one way or the other. So it is important for us to have an understanding of how those devices interact with our network. Okay, let me just check if there are any questions before we move on to routing. Okay, no questions. If you got any questions, just let me know, and I can then be able to cover. Good that I answered your question, Ceci, and then I will try and put a link in the description, but I will have to do it at the end of this class. So if you can check at the end of the class, I'll put a link to where you can find Packet Tracer. But I always encourage people, not encourage per se, the number one skill that anyone in IT needs is the ability to search. And all of us, majority of us, we encounter issues on a daily basis that we've never seen before on our end, but someone else in the world has encountered that particular issue. And when you go online and search, let me just make myself get a bit bigger because now I'm making an appeal for something that I think is very important. So when you go online and search, your ability to be able to search for information or whatever problem you're encountering and getting a solution is, for me, ranks up as one of the highest skills that anyone who is interested in working in IT should have. So whilst I'm going to put the link in the description, I would encourage and implore everyone to use their creativity to go online and find out all this information is available. If you're struggling to get the software from the Cisco website, there are multiple other there are multiple other pages that either can help you on how to find it, how to download it, how to install it, whatever instructions you might want to know. So yes, learn to research. Learn to research. That is the number one skill for me. If you came to me for an interview and I'm the one who's interviewing you, I'm always looking for that particular skill set. If someone can search for something and anything, that person can become anyone and do anything that they want because they've got the ability to be able to go and dig deeper than where most people will not be able to find information. So that's, yeah, don't worry about my rant. I just wanted to just make sure that I encourage you guys, learn to search, because the value is in searching where other people can find information. So let us go back to our class, go back to our lesson. All right, so earlier on, we mentioned that the computer, as it's trying to communicate, needs the MAC address. And for it to learn the MAC address, it goes through a process known as an up request. And now in our case, we are moving on to layer 3, and we are now talking about routing devices. And if you don't know, this is my favorite section. I love routing. That's my passion. So earlier on, we did not have the destination MAC address, but this time around, we now know the destination MAC address. So we've got our source IP address, which is the IP address of this PC, which is 192.168.10.10. And we are trying to get to this server, which is 172.16.10.10. So how does PC A get to server A sitting on this other side of the network? This is representing our serial network, which is signifying our WAN. So this could be a user in one of the branch offices, and we're trying to then access across. So the first step is this PC is going to look at this IP address, and it is going to compare it to its own IP address. Now, that is going to touch on something that we looked at about 2 lessons back when we spoke about IP addressing and subnet masks. And I said to you, the subnet mask is the determining factor of whether an IP address belongs to the same subnet or not. So this PC is going to look at 192.168.10 because it's using a /24 subnet mask. So it's going to look at the first 24 bits. And then it's going to look at the destination IP address and look at the first 24 bits, which is 172.16.10. And it's going to realize that this does not match this. And because they don't match, it simply means that this PC does not reside on the same network as PCA. So PCA then automatically sends its packets to the default gateway because it knows that the destination of this PC is not on its internal network. If the first 3 octets of the IP address were identical, then the PC would then say, oh, by the way, this PC belongs to my network, so I'm going to send this request to the switch, and then the switch will then send it to PC2 that is found on the bottom. But for now, we are looking at layer 3, which is routing. So now the packet gets to the router. Now we're dealing with packets. Layer 3 is packets. So the packet gets to the router. The router then looks in layer 2, the layer 2 switch looked at its MAC address table. The router then looks at its routing table. Right, the routing table basically contains different networks. And then it says, I am looking for a network 172.16.10.0. If it has a route in its routing table, which in our case it has, it is then going to be told that to get to network 172.16.10.10, go to R2 on this particular interface. So in the routing table, it might look something like this. It says go under serial 10, meaning come out of this serial 10 to take you to that. When the packet gets to this router looks at its routing table and says, how do I get to 172.16? And this router says it is known via its internal network. And then the packet then gets forwarded going in this direction, and then it makes it to the particular server. This is how routing works. This is how routing functions. It does not matter how big the network is. This is the principle of routing. And then we're going to then cover the different ways in which routers learn about these particular routes. So let me just pop. So there are many ways in which routers learn about routes. I'm going to call them routes. I'm also going to call them prefixes. It is basically one and the same thing. So you know me, I like examples. If you want to go and buy clothes for an event, you've been invited to a wedding, you got your friends, hey guys, I've been invited to a wedding, I need to buy a suit. Where do I buy a suit? And then John in the office says, no, why don't you go to H&M? They make nice suits. You are consulting someone, they're giving you advice, right? So they're telling you where to go and buy the suit. So that's one way of you learning of where to buy nice suits. The other option is you can go on the internet and type suits and type the location where you are. If you're in London, it basically says suits in London. And then Google is going to give you all the shops that are available. You can read the reviews. So the first one, you asked a friend. The second one, you went online. And these are different ways of you learning about locations of where you can buy a suit. So how does that translate to routing? And how do routers use this particular information to be able to? So I'm going to clear our screen. So the first way, not first in sequence, but one of the ways, is something known as static route. So a static route is when the router is manually configured by someone like you and me, telling it that to get to this network here, go to this. Because remember, there might be multiple routers that this device will be connecting to. And this could be another router going this way. Right, so of all the options, I will hard code and say, if you want to go to this device, go this way, because that is the best path to get to your destination. So you can statically configure a route and tell the router how to behave. The second way the routers learn about routes is by looking at the connected interfaces. So any interface that is connected on the router itself. So in this case, this is interface serial 00, and this is interface gig 0/0. By virtue of the interface being connected to the router, they will then be added into the routing table. So when the router wants to then make decisions, it will look at the routing table and says, oh, this is a connected interface. I'm going to send traffic then flowing through. The third way that routers learn about routes is through something known as dynamic routing protocols. This is when routers form neighborships with other routers on the network, and then they automatically advertise their network prefixes, and then the other routers then get to learn about those prefixes automatically without much configuration. And these are the three predominant. The last one, I wouldn't say it's a way that the routers learn about routes, but there's something known as a default route. And the default route is simply saying anything that I don't know, go to this person. They will then tell you about the information on how to get there. So these are the four primary ways in which routers then operate. So under dynamic routing, this is where we encounter our routing protocols such as RIP, Ospf, Eigrp, BGP. All these are routing protocols that then allow the advertising and the propagation of routing information on our particular network. And we're going to be looking at the different types of routing protocols to try and understand, what metric do they use? How do they behave? What are the differences? If I've got two routes that are being advertised from two different protocols, which one should I choose? Which one should I prefer? And we're going to be covering that, in the next slide. But here we're just looking at the base fundamentals that are important for us to understand when we're basically dealing with routing. Okay, so we're going to start with something known as administrative distance. And administrative distance is basically the trustworthiness of a route. And you got a scale, and the lower the scale, so it's something like this. So we've got this, so this 0, this is probably 200. The lower the scale, the more trustworthiness the route in question. And a typical case in point is there's that one friend or group of friends that you don't trust the information that they might give you. So if that friend came to you and say, hey, by the way, so-and-so passed away, right? At this particular point in time, the queen passed away about 2-3 weeks back. If someone came to you and say, hey, the queen passed away, you'd be like, okay. Because you don't trust that friend, you're probably going to go online and go and double check to make sure that the information is indeed correct. That is the same thing with routing protocols. Not all routing protocols are equal. And to determine the best route, they use something known as administrative distance. The lower the administrative distance, the more trustworthiness is the route. So the scale starts with 0, and 0 is for connected routes. Right. If I were to learn about a route from an interface that is connected to me, I'm going to trust that. If I was to learn about the news from, I was going to say CNN, but maybe nowadays not as much trust with, but back in the days, I mean, if something came out on CNN, if CNN says the queen has died, then you're like, hey, You know, that's true compared to some satire website that might be then publishing. So in a networking context, connected interface have an AD of 0, and static routes have an AD of 1. BGP has an AD of 20. Eigrp has an administrative distance of 90. Ospf has an administrative distance of 110. RIP has an AD of 120. And external Eigrp has an AD of 170. This is external Eigrp. So if a router was to receive multiple routes from different routing protocols that are equal, it will then use the administrative distance to decide which route is the best route. So if a BGP route is competing with an Eigrp route, a BGP route is going to be chosen. Why? Because it has a lower AD than Eigrp. So when we go through the configuration of routing protocols, I'm going to show you the administrative distance in the config. This is one area that you're going to get a question somewhere in your exam because it's a very important subject and you need to know, right? So 0 connected, 1 static, 20 BGP, 90 Eigrp, 110 OSPF, RIP, and maybe not the last one, but the top 5. You need to be able to understand, not only for the exam, but even in real life. Because if you don't see a route getting into the routing table and you're wondering why things are not working, it could probably be the administrative distance. Because if you've got a static route that was configured, but configured incorrectly, and then you enable the dynamic routing protocol, when the election happens, right, static route is going to be preferred, even though it's pointing you to the wrong direction, it's going to be preferred for that destination to Eigrp, which has the ability to take you where you want to go to. Why? Because when you compare the AD, static route is going to have a lower AD than Eigrp. The next one is metric. Now, metric is the value that the different routing protocols use to decide which is a better route amongst themselves. And the metric calculation for the different routing protocols differs. So we're going to look at the metric calculation for RIP. And RIP uses something known as hop count. And what that basically means is that RIP prefers a path with the least amount of hops. So we've got a PC sitting here. Right, this PC connects to this router, and then we've got quite a number of routers that are connected. And let's see, let's put another router here, put another router here, just so that we can be able to, right, there we go, there we go. Okay, so you're trying to get to this other side and you're trying to access this server. So RIP uses hop count. So every count, this is 1, this is 2, this is 3. So to go through this path, it will say it's 3 hop counts. If it goes through this path, it will be 1, 2, 3. And if it goes this way, it is 1, 2, 3. Okay, I was hoping that some path was probably going to be more better. Okay, so we're just going to add another router here, and we're going to add another router here. So this one then becomes 4, and this one becomes 4. RIP by nature will prefer the path with the least amount of hops. It doesn't matter if that path is the most expensive. As long as it has the least amount of hops, RIP is going to use that particular path as its metric. So its metric is based on hop count. So let's take routers aside. I am in Perth and I want to fly to my home country of Zimbabwe. I can either go via Singapore, I can fly straight to South Africa, or I can fly via Dubai. If we're using the metric of RIP, the path via South Africa probably is going to have 2 hops to take me to my destination. And even if it costs me $10,000, and yet the Singapore route is going to cost me $1,000, RIP is going to tell me to go via South Africa because it is the one with the least amount of hop counts, even though it's the most expensive route. So RIP metric is hop count. That's what it uses to make its decision. Eigrp, on the other hand, uses bandwidth plus delay for its metric. And how does bandwidth and delay work? Once again, let's draw a diagram. This time around, we're going to put this one, and we're going to put another router here, network, and a network. So Eigrp then says, okay, what's your bandwidth from here to here? And say maybe you're running a 10 meg link, and then from here you're running a 1 gig link. On this end, you're running 1 gig, but then from here, because maybe it's a satellite link, you are running only 500 kilobits per second. Now, if you were to make a decision based on which one is the best bandwidth coming out of router 1, R1, you probably might pick this path. But however, when you get here, this link is a satellite link, and that link is going to be slow. So what Eigrp does is that it calculates the bandwidth of, let's say, 1 gig plus 10 Mbps, right? Factors that as the bandwidth. And then it also looks at the delay. That is the delay going this way and the delay going that way. And it puts those two together and then calculates what is the best route. So it actually gives you an ability of being able to see beyond just your peering routers and try and see what is beyond and make a calculation. I'm sure many of us have probably noticed that you're trying to go somewhere, and the route that you think is the best route, you get to find out there's an accident that happened. And because of the accident, there's a what? There's a delay. And Google Maps is going to tell you, avoid that route. It might be the best on a normal day, but today is not the best route because there's an accident, and the delay that is there, you're much better off going using an alternative path. And that is Eigrp. So Eigrp uses bandwidth plus delay in its calculation of its own metric. And then the last one that you're going to look at is Ospf. And Ospf uses cost for its calculation. Same diagram again. We got our routers, and then we got our network. So Ospf then simply says the cost of this link, and how does it calculate that cost? It creates a weighting on the bandwidth. So 100 meg link in Ospf might have a score of 50. A 1 gig link might have a score of 10. A 10 meg link might have a score of 100. So depending on the bandwidth of your links, Ospf can then say, okay, fine, it is 5 from here to here, but it is 100 from here to here. And then it uses cumulative cost. So it's 100 plus 5. And then on this end, it's 100 plus 10. So 110 and 105. 105 has a cheaper cost. So then this path is going to be preferred over this path. Same way that you and I make calculations when you're buying air tickets. If I'm going to fly from here to Joburg and my cost is, let's say, for example, $1,000 to get to Joburg, but from Joburg to Harare, it is $100. From here to Singapore, Singapore is closer to me, so my cost to Singapore might be $200. If I made a decision on which path I'm going to take based on the cost of my source, I might have preferred Singapore. But maybe in Singapore, I have a 2-day or 48-hour delay because the next flight that's going to Harare leaves in 2 days' time. So I'm going to get stuck in Singapore for 2 days because I looked at cost. So Ospf then says, I'm going to look at the cumulative 1,000 plus 100 is 1,100. 1,100, sorry. And maybe my ticket from Singapore is going to be 5,000 because the demand is very high. And then the ticket is going to cost me 5,200. So OSPF then makes the two costs and picks the one that is the least cost. So that's how OSPF then calculates on based on metric. And these things are very important because when you now deal with layer 3 devices and configuration, you're going to be anchoring on this particular information if things don't work as per expectation. I'm going to drink water and then we are going to continue. I'm just going to check if there are any questions. Today I'm operating on a single screen, so I can't see the other side. So I need to constantly come back and just make sure, that I am with you. All right. So another question. In case there are more than 2 routers in the network, does the packet have to route through each router, or it can decide on a shortcut to just, all right, let me just put the question on the screen so that others can be able to see it. Right, so say it's saying that if you've got 2 routers in the network, does the network packet have to route through each router, or it can decide on a shorter path? So the best way I can explain this one is it depends how the router is configured. So if this is my PC, and then router 1 is here, and router 2 is here, and I'm trying to get to a server that is connected here, then ultimately I have to go through, I have to go through router 1, and then I have to go to router 2 to get to this particular server. But if I'm trying to find, right, so if this was my topology and router 2 was here, then I don't have to go through router 2. I can either go through router 1. So yes, I can go this way or go that way. But if the router is in line, then I have to go through it. I hope that basically answers your question. I know it's not the best answer that I wanted to give, but I'm just trying to work out, what scenario you don't have to, but if your next hop is going to be determined by that particular router, then you have to pass through that particular router in question. So it's only when you need to go through. And we're going to cover that as we go through our practical and be able to see how this works in real life. So let's continue. So we looked at metric and distance, and now we're going to look at interior gateway protocols versus exterior gateway protocols, IGP versus EGP. So interior gateway protocols, in short, they work within your own autonomous system. And this is the network that you control end to end. So you'll have your domain, and this is your autonomous system. And this is where everything that belongs to that network, you basically control. Let me just bring up my other screen. So that's under your control and supervision. And the common IGP protocols are RIP, OSPF, Eigrp. All these are internal gateway protocols. And then when you want to connect to a different autonomous system, which is usually the internet, you need another protocol that takes you to a different AS. And the one protocol that operates as an exterior gateway protocol is BGP. So BGP is the only exterior gateway protocol, and it is known as the protocol of the internet. So the internet operates and works on BGP. That basically takes us out to the public world. So if someone asks you, which you might come across in the exam, name the interior gateway protocols and exterior gateway protocols, then BGP and E. BGP is exterior, and then Eigrp and the rest are internal gateway protocols. And then we're going to close off by looking at the two types of routing protocols that we have. We have what we call distance vector protocols, and we have link state. So distance vector protocols, they send the full copy of the routing table. Right, so you'll have your routing table with all the routes. The distance vector protocol sends that to the neighboring router and forwards that particular information. And usually by default, they send that information at regular intervals. So RIP sends this routing table every 30 seconds. Whether the other device wants to know about it or it doesn't want to know about it, RIP just sends the entire routing table, and that in itself consumes bandwidth. But I'm sure it'd probably be annoying. Imagine you're my friend, and I tell you, oh, by the way, the queen passed away. Then, oh, okay, 30 seconds down the line, I tell you again, oh, the queen passed away. Okay, 30 seconds, I say the same thing, I say the same thing, I say the same thing. I'm sure you're probably going to get to a point where you get annoyed. And that's how RIP operates. It sends the entire routing table to its neighbors at regular intervals. And it is very slow on convergence. And convergence is if there was a change in the network topology, the time it takes for other routers to know about the change that has transpired. And taking the example of RIP sends every 30 seconds, it means if something happened a second after it sent the routing table, it has to wait for the next 29 seconds before it can send another one. And in between, you have an outage that is happening that can be fixed with that. So that's the distance vector routing protocols. The other one is link state routing protocols. So link state routing protocols, they don't send the routing table. Instead, they provide updates to the respective routers. So this is how link state routing protocols operate. So they send small packets called LSAs or link state advertisements. And in these link state advertisements, they then advertise the networks that the router knows. So this one will advertise, this one will advertise. So they send, and then each router takes all these link state advertisements and adds them to its topology table or database. And then it will then run an algorithm to then determine which is the best path to get to the particular destination. So that's how link state protocols behave. And the most common link state protocol is Ospf, and it uses an algorithm known as the Shikastra algorithm. So it gets all these updates, puts them in a database, and then it runs the algorithm on that to then determine the shortest path to a destination. And then it's that shortest path that is then placed in the routing table. So that's the behavior of different routing protocols. Eigrp is known as an advanced distance vector protocol because, or it's also known as a hybrid protocol because it has characteristics of both. The first part is Eigrp sends the entire routing table at the beginning of the conversation, right? So Eigrp will send you the entire routing table, which is Eigrp. It sends the entire routing table to its neighbor, and then after that, it will send only updates. and changes that might happen on the network. So now it takes the behavior of the link state routing protocol as it then goes through. So these are characteristics of routing protocols that you need to know and understand, because they can not only ask you questions about the different characteristics. The algorithm for Eigrp is known as dual. Yes, it's known as dual. And the algorithm for Ospf is Shikasta. So you might get a question, asking you which routing protocol uses either of the algorithms to be able to function. Okay, so if you're like me, you're probably looking forward to getting to a point where we get to the configuration, but I thought I might as well throw in an example to be able to try and illustrate the whole concept of link state routing protocols. So Google Maps has a giant database, right? And this database contains routes to different locations, how long it takes, and all the things that happen along the lines. So my house is somewhere here, and I want to go to the airport. So I go to Google Maps and then I type my destination, and then bang, I press enter. And then Google Maps then runs an algorithm in the backend that says, from my source to the destination, what is the best route? And then it comes back and it spews out these two routes as the two preferred routes. One of them, distance is what? 42 kilometers, so it's longer. And the other one, it's longer, but the time is shorter. And this one, the distance is shorter, but the time is longer. So if it's gonna pick a route based on the shortest path, it is going to, or the fastest route, it is going to then send me through the first route. If it's picking based on distance, it's going to use the second one. So I just wanted to throw in an example so that we can be able to see how this applies to our day-to-day lives and how we encounter with some of these algorithms that are doing something similar as you would find on a routing device. So without wasting too much time, let us now look at our lab and see what it is that we are trying to configure. Okay, so I'm going to draw this and then we're going to be able to implement it. So what we are trying to achieve is we have a PC sitting here that is connected to a switch. The switch connects to a router. The router then connects to another router. This is going to act as our WAN. And then on this other end, we're going to have a switch. And then we are going to talk to this server that is on 8.8.8.8. And this PC is going to be coming from 192.168.0.0/24. Its IP address is going to be .10. The default gateway is going to be .1. Okay, so success is us being able to access the web server that is sitting on this end. So that's criteria number one. Number two, we should be able to then ping this server. If we can ping it, then everything else is working. Then we're going to look at how we can implement routing. And the first one that we're going to implement a static route. Then we are going to take away that static route, see how that functions. We're going to implement a default route. And then we're going to implement a dynamic routing protocol. And in my case, we're going to configure Eigrp, just because I love Cisco. So we're going to run Eigrp. The whole objective is to see in real life what all this looks like when you're configuring it and getting it to work. So we're going to cross over to GNS3. Erase that. All right, let's cross over to JNS3. Just close that, Cool. All right, so JNS3, just going to eliminate this. Let's start from scratch because I want to make sure that we are, if you are to follow this by yourself, you can be able to follow step by step and be able to get to the same conclusion. So we said we need a PC. So I'm going to devices. I'm going to connect to PC. And we need a switch. So I'm going to go to switches. I'm going to pick a switch. And then I'm going to pick 2 routers. And then this is probably going to answer Ceci's question on how traffic flows when you're dealing with routers on the network. And then we're going to have another switch coming here. And then we're going to close off by putting a server. And I'm going to pick a server coming here. So we'll start configuring the PC. We said our IP address is going to be 192.168.0.10. That's on 255. And because we are going to be leaving our network, going to another network, we're going to need a default gateway. And say the gateway IP address is 192.168.0.1. And that completes our config. Before we go ahead, I need to probably connect this so that this can be able to work. I'm going to connect that. I'm going to connect this router to this router, router to switch, and then switch to the server. Now, we're not going to do anything on our layer 2 switch because the layer 2 switch basically connects devices. So we're not going to touch any configuration. If anything else, we might look at the MAC address table, but we've looked at that in the previous slides. So we're not bothered about that. So we're going to go to our router. And I think what I did not mention earlier on, which I'm probably going to mention now, is so on this side of the network, let's do this. Let's make this a bit fancy. Fill color, okay. So this part of the network is going to be our WAN. Okay, let's skip that. This is going to be our WAN. And okay, my pen, WAN. And here we're going to use 172.16.10.0/30. And this is going to be .1, and this is going to be .2. I just wanted to, yeah, that's part I did not explain earlier on. All right, so let's go to our, so gig 00 is connected to our LAN, and gig 01 is connected to our WAN. So if you go to the router, we need to then connect to the CLI. And I'm just going to erase this on the screen just so that we can see. I'm just going to make this a bit bigger. Right, I'm connecting to this device for the first time. So it's asking me if I want to auto-configure it. I don't. So I press no. And this is what you encounter on a normal router in a production environment. So enable configure terminal for Cisco devices, and interface gig 0/0 is going to have an IP address of 192.168.0.10 with a subnet mask of 255.255.255.0. Press enter. You're going to give it a description. This is the LAN interface, so that when we look at it at a later point, we are not confused. We know what that interface is. And we're going to exit, and then we're going to configure the one side of the router. And we say the interface is interface gig 0/1. IP address is going to be 172.16.10.1. The subnet mask is a /30, so that's going to be 255.255.255.252. And this is the reason why I was saying earlier on in previous videos, you need to know your subnetting because you're going to deal with this quite regularly. Now, router interfaces by default, they're shut down. So we're going to do a no shut. And I need to do the same thing on interface gig 0/0. And I'm going to do no shut. Right. So one thing I need to also do is I need to name the router so that it's easy for us to identify when we're working on the different routers. So this is going to be R1. So now it's called R1 back. Show IP interface brief. I want to see the status of my interfaces. So my gig 00 is up and running with an IP address of 10. Sorry, the IP address is incorrect. So here it was supposed to be 192.168.0.1. So I need to go back and fix that. Interface gig 0/0. The IP address is going to be 192.168. It's not there. Let me put it. IP address is 192.168.0.1, 255.255.255.0. Okay, so that's the first router is done. And I need to just go to my PC and just make sure that I can ping that particular router before I can then attempt anything else. 192.168.0.1. That's my default gateway. Can I ping my default gateway? Let me just stop the simulation. Let's just go to real time. Right. Let's see if we are having any luck. Things seem not to be working. Okay. So that brings us to some troubleshooting. All right. I'm just going to try one more time. 192.168.0.1. Okay. Doesn't seem to be working. I was not expecting to be troubleshooting this, but this is what you encounter in real life, right? So let's troubleshoot together. And I'll just show you my troubleshooting steps to try and see how best I can try and resolve this. Okay, so I'm going to start by just checking that my IP address on my PC is correct. So I'm just going to come here and then do, oh, by the way, there we go. The packet then eventually came through. Okay, so I think I know what transpired. I suspect that spanning tree was happening between the router and the switch. That just delayed that. So let's just confirm that we can see. Okay, so now we can see our router on the LAN side. If you can't see your gateway, then you can't go to the next step. So we've confirmed that on the LAN side, everything else is fine. So let's go to router number 2 and go to CLI, and then we're going to do the same thing that we did. And no enable, I'm going to do this a bit faster. Interface. Let's see what our interface is. Gig 00 is the WAN side, gig 01 is the LAN side. Okay. So gig 0/0 description is WAN. IP address is going to be 172.16.10.2 on 255.255.255.252. Then no shut. That interface has come up. And then gig 0/1 is going to be the LAN side. So description is LAN. And then our IP address is going to be 8.8.8, 8.8.8.1, which is going to be the gateway, 255.255.255.0. And then we're going to do a no shut. Okay, so now the router should be able to ping the corresponding. So let me just change that to the host name, R2. So R2 is trying to ping R1. So ping 172.16.10.1, which is the other side, and I should see a reply. Okay, so I got 80%. The first one was probably app being resolved, but after that, everything else seemed to be working fine. Let's just double check. So all 5 packets are going through, no issues. So all that, what I'm just basically confirming, if I were to minimize this, is I can talk from here to here and from here to here. So this part of the link is working fine. We tested from the PC all the way to the router and confirmed. And I would encourage you to do the same thing just on your networks, right? When you're troubleshooting, try and see where in the flow your issues might then be happening. All right, so we've done that. I'm going to close that. The next part is going to be the server, and the server is going to use an IP address. You said 8.8.8.8. So the configuration here, IP address is 8.8.8.8. Subnet mask is going to be a 255.255.255.0, and then the gateway is going to be 8.8.8.8.1. And I'll close that. That should be fine. Okay. Let us confirm that we can see the default gateway from this server. So we're going to ping 8.8.8.1. And yes, the server can see its default gateway. So from a network standpoint, our network should now be solid enough for us to start doing the testing that we need. Why? Because the PC can see the router, the routers can see each other, and the server can see the router on the other end. So that should be good to go. So before we do anything, let's go to PC1. Let's see if PC1 can ping the IP address. Remember, our criteria was we need to be able to ping 8.8.8.8 from PC1. So let us see if PC1 is able to succeed. I'm just going to clear my screen. CLS. Oh, okay. It's refusing to work anyway. So I'm going to ping 8.8.8.8, and I'm being responded by an error that the destination host is unreachable, meaning that it can't reach the other side. So let us go to our routers and try and work out what's going on. Why can't we reach the other side? So we need to look into our routing table. Remember, we said routers basically forward packets based on the routing table. So R1 must have a route to the 8.8.8 network. If it doesn't have a route to that network, nothing is going to work. So how do we check the routing table on a routing device? We show IP route. Now remember, I said that routers learn about networks in different ways. The first one was static routes. The second one was connected interfaces. So if you look at the routing table, we know that this router has learned about the 172.16.10 network, and it has learned it directly because it is directly connected to the what? To the device. And that interface is gigabit 01. So in our routing table, we only have two routes: how to get to the 192.168.0 network and how to get to the 172.16.10 network. That's the only route, but we don't see the route for the 8.8.8 network because it's not there in the routing table. So how then do we get that route in the routing table? We said we can use static route. So in this first part of the lab, we're going to use a static route. And how do you configure a static route? On a Cisco device, you go into the configuration mode, conft, and you type the command IP route. And then you specify, you can either put a question mark, and then it will ask you that you need the destination prefix or the destination network. So where are you trying to go to? And in our case, we're trying to go to 8.8.8.0. And then it will ask you for the subnet mask. And our subnet mask is 255.255.255.0. And then what is the next hop to get to that network, right? Where do I go to get to that particular network? And I can either use the next hop's IP address, or I can use the exiting interface to get to that point. And I'm going to use the IP address so that it's much more clear. So we're going to use 172.16.10.2. That is our next hop. Now, if we look at our routing table, show IP route, we now have a route, we now have a static route to get to the 8.8 network. But does that fix our problem? Can I go to my PC and be able to ping that particular destination? Let's give it a shot. This time around, I'm not getting a destination host unreachable. I'm getting a request timed out. And not at all times, but most of the time when you get a request timed out, the issue could be you have a route going to your destination, but it does not have a route coming back. So you know how to get there, but it doesn't know how to come back to you. And that's the one disadvantage with static routes. You have to manually configure them on every device along the path in order for things to function. So we need to then go to router 2 and tell router 2 how to get to our internal network so that the reply traffic can then make it in our direction. So let us go to router number 2. And in router number 2, okay. Router number 2, we need to configure the reverse. So conft IP route to get to the 192.168.0.0 network on 255.255.255.0. The next hop is 192.16.10.1. So now we have told router 2 that to get to the other side of the network, it needs to go to router 1. And now if we look at the routing table, we can now see that router 2 now knows about the 192 network via static. And then if we go to our PC and try and ping, this time around we're getting a reply. So now we can now reach the web server, but remember we're supposed to reach it on two criteria, the ping, and we should also be able to access the web service. So if I go to my desktop and close that and open up a web browser, and that's the beauty about Packet Tracer, right? It's got all these features available, so you can test multiple scenarios. It's just taking a bit of time to process. Oh, come on. Yeah. You get this once in a while. Things just don't work as you might wanted them to work. All right, let's go. All right, so this is our web page. So we're going to type 8.8.8.8.8 and then press go. And this is the web page that is opened. And that web page is opening on the other web server. So now we can connect to our network via a static route. So we configure the static route in order to get us to communicate on the other end. And we also highlighted the disadvantages of static routes and advantages. The other disadvantage is that if router 2 went down, the static route is not going to remove itself from the routing table. So it's always going to be preferred because it is thought to be the best route to the destination. Earlier on, we spoke about administrative distance, and I said the AD for a static route is what? Is 1. This is where you see the administrative distance of a routing protocol. So when you configure Eigrp, you're going to notice that the AD of that Eigrp is going to be an AD of 90. So let's just erase that, return. So we're going to take away our static route and we're going to configure Eigrp. But before we do that, we're going to test to make sure that our static route has stopped working. So I'm just going to go conft, then if I press the up arrow, there's my static route, Control A, no IP. There we go. Control A, no IP route. So in Cisco devices, if you want to remove a command, you just type no, followed by the command that you basically type. So we've taken away the static route on R1. Let's go do the same thing on R2. Right, so the static route has been taken off. So now, if you go to PC and try and ping the server, that ping should not work because we have taken away the static route. So ping 8.8.8.8 and destination host is unreachable because you have taken away the static route. So I'm just going to close that. So now we're going to configure our routing protocol and we're going to be using Eigrp. So to configure routing protocol like Eigrp, the command is router Eigrp 1. 1 is the autonomous system, not important for Network Plus. Oh, by the way, what I'm doing right now is not covered in the syllabus. I'm just at least giving you practical hands-on skills on how you would configure a static route on a Cisco device and practical hands-on skills of how you can configure a routing protocol. So that if you want to practice, you can be able to practice, get the muscle memory, and it will help you in your troubleshooting when you have a full understanding of how the routing process works. So router Eigrp, and to advertise networks in Eigrp, we use the network command. So on R1, we're going to be advertising. When you're advertising a network, you're choosing the network that you want to tell the other neighbors about their existence. So we're going to advertise the 192.168.0.0 network on a mask of 255.255.255.0. So we're going to advertise that network, and then I'm also going to run Eigrp on the one interface. So we're also going to use 172.16.10.0 on 255.255.252. All right. So we have enabled Eigrp on router 1. We have to go and do the same thing on router 2. So I'm going to minimize this on router number 2, maximize that. We're going to router Eigrp 1 network 172.16.10.0 255.255.255.252. We have formed neighborship, so the two routers R1 and R2 are now neighbors, and then we need to advertise the 8.8 network 255.255.255.0. Let's enter. Okay, so let us check on R2 if it knows about the 192.168 network. I'm going to show IP route, and indeed the 192.168.0.0 network is now learned via Eigrp. And how do I know? A route with a D is an Eigrp route, as you can see, and also the administrative distance of 90, which then signifies that it is an Eigrp route. And if I go to R1, I should now know about the 8.8 network from Eigrp. Let me just get that done. So the neighborship is formed. Let's double check the route. Show IP route. And I now know about the 8.8.8 network. And if I then go to my PC and try that ping one more time, maximize that. Up arrow, ping 8.8.8, and now that is responding. And if we try going to the web page, okay, that's the one that was acting up and caused my machine to crash the last time. So that is working, and it is working because we have configured a dynamic routing protocol between the two. So we have demonstrated that you can either advertise or learn about a route through a static route, or you can learn about the route through a dynamic routing protocol such as Eigrp. The good thing with dynamic routing protocols is that as networks increase, right? So if we went and created another network on this router, it did crash. Okay, it crashed and then bounced that. So if I show IP Eigrp neighbors, you'll notice that I have a neighbor whose IP address is 172.16.10.1. But the part that I wanted to show you was if we had a new network, let's say loopback 1, and then we're going to give it an IP address of 4.2.2.255.255.255.0. And then we're going to go into Eigrp and advertise that route. So network 4.2.2.2.0.255.255.255.0. When you go to router 1, we didn't do anything on router 1, but if you show the IP route on this router, you'll notice that we now have the 4.22 network being learned from R1. So dynamic routing protocols are good for that because you configure once and they'll propagate that prefix for you and advertise it to numerous routers across. And if anything was to happen, they will also withdraw that route and stop it from being advertised. So where possible, try and use dynamic routing protocols, but there are some instances where you need to configure static routing protocols in order to get things to be able to work. So that's how routing protocols function. We're not going to cover OSPF. Like I said, this is out of the syllabus for Network Plus, but I felt it is very important for us to be able to see how things work. I can't reinforce enough tools like Packet Tracer, why you need them, because they then help you in such situations, and you being able to then learn on how you be able to then implement. So that basically, wraps us or brings us to the end of today's class. I wanted to cover quality of service, but I figured we have spent so much time just going through this. QoS is a very important topic that you don't want to get it to ride on top of something else. So in the next class, which is going to be running on Monday, I am going to be covering quality of service, and then we're going to be looking at Ethernet technology. So we're going to be looking at layer 2 and go more in detail on things like Ethernet and how those things function. So if you are watching right now and if you've got any questions, this is the time, to ask any questions that you might have. And just a second. What just happened? Okay, I'll leave that on the screen. I don't know why. Okay, I think I know what's happening. Anyway, let me just leave that on the screen. Okay, so if there are any questions, I think on my end I might have covered everything I wanted to cover. If there are no questions, then I thank you for taking your time. Once again, we are almost getting halfway of our 6 weeks that we're going to be running. I think the next lesson is going to be lesson number 6, which takes us to the halfway point. If you got any comments, if you think I'm moving a bit slow, I'm moving too fast, don't hesitate. Let me know. You can send me an email. I'll be able to respond to that email. But if there are no questions, Ceci, thank you for the questions. I hope and trust that I answered you. If I did not answer you appropriately or in a way that you're fully satisfied, don't hesitate to send me an email. And my email is in the description below. Let me just bring back the main screen so that we can have a chat. Yes, so my email is in the description below, so don't hesitate to get in touch, and I'll be more than welcome to, get back to you. And somewhere towards the end of the course, I'm probably going to do 1 or 2 videos on just things that I feel are very important for people that are starting their journey in the network industry. That will probably help you, succeed and do well. I haven't been receiving much questions. I hope and trust that you guys are comfortable. But yeah, I would love to receive questions from you guys on anything relating to networking, and I can be able to give my feedback and my 2 cents. Once again, thank you for taking your time, and I will see you in the next lesson.